Okay, so the first bit of news is lab exam 1 is this week during the lab period. This is an individual test. So you're not doing it with your groups. But the questions are going to be very similar to the questions that I've asked on the lab worksheet so far. Yeah, and I don't have your exam 1s graded yet, but I should have them graded on Wednesday. So I'll get them back to you on Wednesday. Anybody have any questions about the lab test?
How long do you think it's going to take?
Yeah, that's a good question. I'll bet, I think at most it'll take an hour. I think people will be leaving probably with the first people will probably be leaving within half an hour. That's my guess. And then you're done for the day. So once you hand it in, you can just leave. We're not doing any exercises after that. Yes?
Just how many you've gone up to this point?
In the labs, that's right. So no calculations from class or short answer questions on the lectures or anything like that, just on the lab stuff. Yes?
Kind of unrelated to this, but will we get back our exam 1 and quiz 1, like the actual sheets of paper to see if we got something wrong and what we got wrong?
Yes.
Okay.
Have I given back any of your quiz 1 yet? Nobody's gotten one back? Okay, I guess I have those sitting around. I guess I'll bring them in with the tests on Wednesday.
Thank you.
Sure. Any other questions? Okay. Well, today I'm just planning to go through some example problems of 2D kinematics problems, give you some time to work on them. You know, it's just a chance to sort of sort this stuff out. So let's get started. Okay, so the first example. So let's say that an object is launched 40 degrees above the horizontal. With a speed of 10 meters per second from a height of 1 meter. And we want to first figure out what's the object's position vector when it reaches its highest point. And then second, what's the displacement from where it is at its highest point? Actually, I'm sort of wording this backwards. Let me say from where it's released to its highest point. So I'm going to go through this one first just to sort of refresh your memories on this stuff. And then after that, I'll go into some and give you time to work on them. So I'm going to start out by just sketching what's going on. This object is launched from a height of 1 meter off the ground. it's launched at an angle of 40 degrees above the horizontal, so this angle is 40 degrees. And the path it's going to take will look something like this. It'll start out parallel to that starting velocity, and then it'll follow a parabolic path until it hits the ground. And we're trying to figure out the position vector here, and then we're trying to figure out the displacement vector. Okay, so in problems like this, what's the first step you take?
Zero position.
Right. Exactly. So we have to choose our, now we're in 2D, so instead of zero position, it's an origin of a coordinate system. And we're going to choose the orientation of the coordinate system. And then we're going to choose when the stopwatch clicks on and off. So I'm going to put the origin where I pretty much always do. That is on the ground or on the lowest point that's referred to in the problem, right underneath where the object is at the start of its motion. So that's going to be my coordinate system. And I'm always going to put the y-axis up. And then time equals 0 is going to be the instant that it's launched. And time final is going to be the instant that it reaches its highest point. And now we can start listing out what variables we know and what we're looking for. Do we know what the stopwatch says when it gets to the highest point? No. Do we know the acceleration? In free fall, we always know that. If your y-axis is up, which I always do, then it's going to be 0 for x, negative 9.81 for y. Do we know the position at time 0? Yeah, right. It's going to be 0 for x, 1 for y. Remember that the position, you can always just think of that as the object's coordinates. So you can see, like, if you plotted this point here, it would be at 0, 1. So pi is 0, 1. Do we know p final? No, that's what we're trying to find. I'll put that over here as a vector. We're going to have to do that one by one. We can't solve for two components in a single equation, but we want to do those both. Do we know the velocity at time 0?
Yes.
Yes, we can figure that out using the angle and the speed. So we're going to do that like this. If I draw the coordinate system, and put the tail of the vector at the origin, we know that this vector has a length of 10. To go counterclockwise from the x-axis, you have to go 40 degrees. And so this is going to be 10 times the cosine of 40, 10 times the sine of 40. And so that comes out to be 7.666, 6.43. And do we know anything about the final velocity? We know one important thing about it.
It's 0.
The y component is 0. That's right. So we know that VFY is equal to 0. We don't know that VFX is equal to 0, and so I'm just leaving that off. So remember, that was the picture I drew of the guy getting hit in the back of the head with a baseball. That x component is not going to be 0 at the highest point generally. Okay, so we want to calculate Pfx and Pfy. We can do it in any order. So you can just ask yourself, is there, can we calculate either one of those? I think we can calculate Pfx using this equation. No. Okay, so 2a, no, it's Pfy we can calculate this way. 2ay times the quantity Pfy minus Piy is equal to Vfy squared minus Viy squared. And you can check to make sure this works. It has Pfy in it, and then go through all the rest of the variables in it, and they have to be known. Ay we know, Piy we know, Vfy we know, Viy we know. So we can do this equation. So we have 2 times negative 9.81 times the quantity Pfy minus 1 is equal to 0 squared minus 6.43 squared. So I'll rewrite this as negative 19.62 times the quantity Pfy minus 1 is equal to negative 41.34. Now divide both sides by negative 19.62. You get Pfy minus 1 is equal to positive 2.11. Now add 1 to both sides, and you get Pfy is equal to 3.11 meters. Any question about that first part? All right, so now we want to calculate Pfx. And so is there an equation that lets us calculate Pfx? It turns out there isn't one. So no equation works for Pfx. And so we want to find Tf first. I think the equation we can use for that is Vfy is equal to Viy plus Ay Tf. It has Tf in it. We know Vfy, Viy, and Ay, so this one will work. So 0 is equal to 6.43 minus 9.81 Tf. And so Tf is equal to 0.66 seconds. And so now that we know one more variable, now we can look for an equation that lets us calculate Pfx. And we can use Pfx is equal to Pix plus Vix Tf plus 1/2 Ax Tf squared. One thing you always have to be careful of in the x equations is we're used to, in free fall problems, putting negative 9.81 in for for the acceleration, but that's only the y acceleration in 2D. The x acceleration is 0. So when you get to this x equation, this whole term just goes away. There's no acceleration in x. Okay? So we have PFX is equal to 0 plus 7.66 times 0.66. And so PFX is equal to 5.02 meters. And so the final position, the position at the highest point is for X 5.02, for Y 3.11. So that says that when it reaches the highest point here, if you draw this vector that goes from the origin to the highest point, that vector has a horizontal, this is 5.02 and this is 3.11. Any questions about that? Okay, so now what about the displacement? So now we want the displacement from where the ball is released to the highest point. Remember that the displacement vector is just the later position minus the earlier position. So this is 5.02, 3.11 minus 0.1. And so that displacement is 5.02, 2.11. Okay, so let's visualize what that means. So let's say that this object follows a path like this. The displacement vector is the vector from the earlier location to the later location. So this is the displacement vector. Notice that's not the same vector as the position vector. They almost look the same, but the position vector went from the origin to this point. The displacement vector goes from the earlier location to the position at time final. And so what this means is if you draw this right triangle, this distance is 5.02 and this distance is 2.11. Any questions about that? Okay. Let's do another one. So let's say you're on a skateboard going across the floor at, what did I say? 5 meters per second. Okay. That's you. And at some point, you drop an object from 1 meter off the ground. And over here somewhere is a little cup that has a height of 15 centimeters or 0.15 meters. Okay. And the question is, so 5 meters per second is the speed. How far away from the cup horizontally should the ball be dropped to land in the cup? Okay, so first of all, one thing you need to check is make sure you're picturing what's going to happen right. If this person is riding along on a skateboard, and let's go with this object, that object isn't going to fall just straight down. Remember that that object, at the instant it's released, is going to have the same velocity as the skateboard. Okay, so this object is actually going to start out horizontally and then follow a parabolic path. And we want to know what this distance is. Okay, so the first thing we need to do is choose the coordinate system origin and orientation, and then the 2 times. So I'm going to put the coordinate system on the ground, right beneath where the ball is released. Time equals 0 is going to be the instant it's released. Time final is going to be the instant that it reaches a height of 0.15 meters. And now I'm going to give you a minute or two. See if you can fill out what variables we know and what we're trying to find for this. Okay, did any equation work for this? No, so we have to find time final instead. Okay, so okay, so now we have to find t final. So take a minute and see if you can find an equation that'll let us solve for t final. The one we can use is the one that is the most common for solving for t final before you go back to solving for what you want. And that's the y component of the position equation. So pfy is equal to piy plus viytf plus 1/2 ay tf squared. So you can see it has tf in it. We know pfy, piy, viy, and ay. So this one will work. So 0.15 is equal to 1 plus 0 times tf is just 0 minus 4.905 tf squared. We don't have to use the quadratic formula for this because of the zero term in the middle. So we can just use the square root for this. So we get 4.905 TF squared is equal to 0.85. And divide both sides by 4.905, take the square root. You get the time final is equal to plus or minus 0.416 seconds. And then do we want the positive or negative time final? Positive. It's easy with time if one of them's negative because we only want positive times in this class. And so now that's one more variable we know. You know, you can put it in here in your table. And then I guess take a minute again and see if you can figure out what equation we're going to use to get the answer that we want. Now we can use PFX is equal to PIX plus VIXTF plus 1/2 AX TF squared. So PFX is equal to 0 plus VIX is 5 times 0.416. AX is 0, so this whole term goes away. And we get that PFX is equal to 2.08 meters. So if you drop this ball exactly 2.08 meters away from the cup horizontally, it'll land in the cup. Any questions about that? Okay. The next thing I want to show you, so do you remember I mentioned earlier in the class common misconception number 1. Do you remember what that was? So I'm going to, throughout the class, give you a handful of things where like your intuition about how this works is most likely wrong, and you're going to have to sort of consciously tell yourself not to believe that anymore, you know. The first one was when I showed you the video of the feather and the bowling ball. Do you remember what the misconception was?
Gravity makes heavier things fall.
Yeah, that's right. So it's often believed that gravity makes heavier things fall faster. It's not true. Well, in a way, it's sometimes true that heavier things fall faster, but it doesn't have anything to do with gravity. It has to do with just interaction with the air. And so now I'm going to give you the second common misconception. And this one is that it's often believed that an object's horizontal speed affects how quickly it falls. In fact, objects fall the same whether they have horizontal motion or not. Okay, so this one also takes a little time to get used to. And so here's what I'm saying. So if you had somebody fire a bullet out of a gun horizontally, at the same time that somebody from the same height just dropped the bullet, okay? These two bullets would hit the ground at the exact same time. One is going to hit the ground a long way away, you know, many hundreds of yards away, and one is just going to land right at their feet. But if you time them, it should take the exact same amount of time. And I think that doesn't feel right to most people, but it is the case. Okay, so I want to show you a video of this. Let me find it. Okay. So here we go. This is a Mythbusters thing where they actually rig up a system so that a bullet is dropped at exactly the same time another bullet is fired horizontally. And they set it up so the fired bullet is going to land at the exact same place as the drop bullet. And what we're going to see is that they hit the ground at the same time. Oh, whoops. I always hit the wrong one. Okay, so kind of surprising. One thing I should say is, like with the feather and bowling ball thing, this can be messed up by interactions with the air. So this is 100% true if there's no air resistance. The less air resistance affects the motion, the closer these are to true. But there are cases where, like, for example, one that I think people often think about is like, well, wait, what about a Frisbee? That doesn't make any sense, like, because if you drop a Frisbee, it hits the ground way before if you throw a Frisbee horizontally. But that's because of air interaction. The Frisbee is designed to stay in a shape that gives it a little bit of lift as it goes. And the other thing is like a paper airplane, If you throw a paper airplane, it doesn't hit the ground as fast as a crumpled up ball of paper. But that, again, is because of lift and air resistance. Yep.
And that's only if the gun is being fired like straight ahead, right? What if you were
Yes.
shooting it like up?
Yep, and we're going to do that calculation now because the one thing about this that they talk about it as if there's a difference of 39 milliseconds between how long it takes, like, okay, they're pretty close to exactly the same, but not quite. I think probably the more likely thing is that getting a bullet to fire exactly horizontally is hard to do, I mean, okay, like or let's say if you think of it as a continuous range from like 1 degree down to 0 degrees, it's impossible to get it exactly at 0 degrees, maybe you could get it at 0.04 degrees or something tiny, but you're never going to get exactly 0 degrees. So I want to do a calculation where and show you how it looks in the math to show that, yeah, it's the exact same thing if you're trying to calculate how long it's going to take for a horizontal bullet to hit the ground compared to drop. But then I'm going to put it at just a tiny little angle, okay? I'm going to put it at, let's put it at 0.1 degree, okay? 1 degree is pretty hard to eyeball. 0.1 degrees is impossible to eyeball. And you're going to see that there's a surprisingly big difference in the amount of time it takes for that to hit the ground just because of that little change in angle. Okay, so here are the calculations. So let's calculate it first for a bullet dropped from 1 meter off the ground. So this is just going to be a one-dimensional free fall problem like this. And I'm just going to go back to using the one-dimensional approach. So I'll say that my 0 is going to be at the ground. My positive is going to be up. My negative is going to be down. I'm going to choose my time equals 0 instant to be at the instant it's dropped. And my time final to be when it reaches ground level. We want to find the final time. The acceleration is negative 9.81. The initial position is positive 1 meter. The final position is 0 meters. The initial velocity, what's the initial velocity if it just dropped? 0, yep. And we don't know the final velocity. And so we'll use the equation PF is equal to PI plus VITF plus 1/2 ATF squared. So 0 is equal to 1 plus 0 minus 4.905 TF squared. And so 4.905 TF squared is equal to 1. And TF is equal to plus or minus 0.452 seconds. And we want the positive one. And now I'm going to do a bullet that's fired horizontally. So, and I'll just give its speed a nice round number. So let's say the bullet's fired horizontally from 1 meter high and with a speed of, let's just call it 1,000 meters per second. And we're going to calculate how long this is going to take to hit the ground. So this time it's going to start at a height of 1 meter. This time it's going to start out horizontal and then take a long parabola like that. Its starting velocity is going to be a horizontal vector of 1,000 meters per second. Okay, so the first thing we have to do is choose a coordinate system. This is a 2D problem now. So coordinate system, I'm going to put like this. Pretty much always my approach. And then again, the time equals 0 is going to be when it's fired. And time final is going to be when it reaches ground level. We're looking for time final. We know that the acceleration vector is 0, negative 9.81. The initial position vector is 0, 1. The final position, we only know the y component. We don't know how far away horizontally it's going to be, but we know this is going to be 0 meters. And now what about the initial velocity? Well, you can draw the coordinate system and then draw the starting velocity vector with its tail at the origin. And it's just perfectly horizontal like this with a length of 1,000. So what are the components of that vector? 1,000 for x, 0 for y, right. It's just the coordinates of the head of the vector. And so this is 1,000, 0. And the equation we can use to solve for time final is this one. PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. And this says 0 is equal to 1 plus 0 minus 4.905 TF squared. And notice that now this equation in this form is the exact same equation that we got in the dropped case. 0 is equal to 1 plus 0 minus 4.905 TF squared. So everything, we put in exactly the same values in all the same spots. There's no way to get a different answer. And so time final is positive 0.452 seconds. So those are exactly the same. If that bullet is fired horizontally. Okay, so now let's see what happens if we tilt the gun up just a tiny little bit. Okay, so let's do 0.1 degrees. So what if the bullet is fired uh, 0.1 degrees above horizontal? Okay, so this time it'll look something like this. Okay, so the bullet is fired here. Say this is horizontal. And we're just going to be barely above, that's very much exaggerated for an angle of 0.1 degrees. And it's going to start out like this and then follow a parabolic path until it hits the ground. This is 1 meter. And so the fact that it's going to start out going up a little bit before it gets to its highest point, that's the extra time that it's going to add. And then the fact that it's going to be higher than where it was shot from when it gets to the highest point. Okay, so go through the same steps. So there's the coordinate system. Time equals 0 is going to be when it's fired. Time final is going to be when it reaches ground level. We're still looking for time final. The acceleration is 0, negative 9.81. The initial position is 0, 1. The final y position is 0. And now the thing that's different this time is the initial velocity vector. And to figure that out, here's the coordinate system. And again, I mean, that's a super exaggerated, I can't draw a 0.1 degree angle, it's too little, but this angle here is 0.1 degrees. And this length is 1,000. So that VI is going to be 1,000 times the cosine of 0.1 and 1,000 times the sine of 0.1. And what you get here for the velocity components are, for the x component, 999.998. Okay, so very, very close to just a horizontal 1,000. And then the y component is 1.74. And we can use the same equation again. We can use PFY is equal to PIY plus VIYTF plus 1/2 AY TF squared. Plug in the values. 0 is equal to 1 plus 1.74 TF minus 4.905 TF squared. And now use the quadratic formula. And you get that TF is equal to, you're going to get two answers. One is negative, and we don't care about that one. And then one is positive, and that's the right answer for what we're looking for. So remember how long it took for the bullet to hit the ground in the other case? It was 0.452 seconds, okay? This time, by just being off by 1/10 of a degree, the answer is 0.663 seconds. So that 1/10 of a degree increased the time that it took to hit the ground by about 50%. Yep.
Out of curiosity, since we know the difference between the time final of the Mythbusters experiments, is there a possible way we could, assuming the
Yeah.
difference is degrees, find out what the degree is of the delta?
Yeah, that's a good question. We could do that using inverse trig, which we don't really do in this class, but yes, we could totally do that. I mean, we could put this in. Here's how you would do it. Your initial velocity, I'm going to erase this because it'll be confusing in here, but your initial velocity would be 1,000 times cosine of theta, 1,000 times the sine of theta. And then you would put this into your equation as your initial velocity. And then you could do the quadratic formula and use inverse trig to find what that angle is. Yep. Any other questions? And so you might wonder, you know, if there's an easy way to put your finger on what it is about this that makes that time increase so much. The important thing, the thing that came into the equation and changed everything, was the y component of the initial velocity. Okay, and so the math comes out to be exactly the same as if you started with an object 1 meter off the ground and threw it up into the air with this as a starting speed. Okay, which is about like, what's that, 4 miles per hour, you know? And so if you threw something 4 miles an hour up in the air, it would go up this high before it came back down, something like that. And that's what this does. Any questions about that? Okay, let's stop there.